Okay, so up next is limits by direct evaluation, and these aren't as bad either. These are when you can just sort of plug the number in. In fact, if you don't have a graph or a table to look at visually, direct evaluation is the very next best thing. When you are able to directly evaluate, that means you've got a function there that is a continuous function, that there aren't any breaks or holes or gaps or anything funny in it. And this is just a regular cubed function, and you've learned in the past that that's just something that sort of has that kind of feel to it. Hopefully you remember that. But if we're asking to find a limit of a function that doesn't have any breaks or holes or gaps or anything in it, then I just plug the numbers in, and my limit would be 2 cubed minus 3 times 2 squared minus 2, and I really just have to figure out what that equals. So I get 8 minus 3 times 4 minus 2, so 8 minus 12, it's negative 4 minus 2. I think that's negative 6. I'm going to do the math again because I'd hate to give you the wrong answer. So I get 2 cubed is 8, I know that for sure, plus or minus 3 times 12, minus 3 times 4, jeez, what's wrong with me? Minus 2, and yep, negative 6, so I double checked it on the calculator. So negative 6 is the value. I don't have somebody in the background yelling at me, hey, isn't that supposed to be filling it in? So I just want to make sure that I get the values right for you. So direct evaluation, exactly as it sounds, plug it in. So when we look at problem number 16, we might be thinking, okay, well, 0, where do I plug 0 in? If I don't have a variable, there's no x in there, what that means is that this is a graph where, I'm going to pick a different color so it stands out, where the function is always equal to 1. That means no matter what x is, y is 1. So that would be this graph here that crosses the y-axis at 1, just a line. And it doesn't matter where I'm looking when I'm finding the limit, but in this case they said focus at 0, so I'm going to focus at 0. I'm going to look at 0 on both sides of 0. Where is this pointing? It's pointing exactly to where the graph always is. And so my limit is what the graph always is, and that's 1. So when you get a constant, this is something to kind of keep in your knowledge bank. The limit as x approaches anything, any number, it doesn't matter. Let's make it a. For any number of some constant, it will always equal the constant. So if there's no variable in there for me to work through. So that's kind of an always fact. All right, so plugging in for x, not so bad. When it's a constant, it's just the constant. Sometimes it's a little scary, but what I do is still the same. I'm going to plug it in. Now, this one might bother some of us because we know what tangent looks like. Tangent looks like this, kind of. I'm just doing a quick sketch of the parent function of tangent. Doing my best here. Okay. And this is not continuous. There is an asymptote here. In fact, there's infinitely many asymptotes if I continue this tangent graph forever and ever and ever. But the limit is taking place at pi over 4. That's where I'm evaluating it as x approaches pi over 4. Well, the first asymptote here is at pi over 2. If you look back at your notes from graphing trig functions, that first asymptote on the parent function is at pi over 2. And so at pi over 4 right here, the graph is continuous. So again, I can just find the value of this. That 2 in front of there changes that number on the amplitude, and it'll change our number when we do our value. So by direct evaluation, I'm doing 2 times the tangent of pi over 4. Again, I'm going to have to go back to my trig days. What's the tangent of pi over 4? Well, the pi over 4 family is the square root of 2 over 2, comma square root of 2 over 2, and I put the sine over the cosine, so it's square root of 2 over 2 over square root of 2 over 2. And some of you might be yelling, it's 1, it's 1, I know it's 1. It is. So this is 2 times 1, or 2. And so my limit here, made that equal sign up a little high, is 2. And again, even though the function was not necessarily continuous all over like a cubed function was, it is continuous where we're interested in, and that's right here at pi over 4. So here's another kind of thing that might come up that may bother some of you, but don't let it. What if I'm looking at a limit from the left or from the right, and this one is saying find the limit as x approaches 1 from the right? Well, again, if it's a continuous function, and this is just a parabola. This parabola looks like this. It opens up, and there is going to be a point at x equals 1 somewhere on this graph, and on each side of 1, it's going to go exactly to that same point. I'm not exactly sure where 1 is on this parabola, but I do know that at 1, it is going to approach the same value on both sides. So I can, even though it's from the right that I'm looking at, I can still just plug this in. This is 4 times 1 squared plus 2 times 1 minus 3. The only time I would have to be worried about this is if I don't have a continuous function. And so 4 times 1 squared, that's 4 plus 2 minus 3, 6 minus 3, so my limit here is 3. Again, it doesn't matter that it's from the left or the right because this function right here is continuous and it's always going to be going to the same place. So now let's get to some of them where we don't really know if it's continuous. So we're going to do our direct evaluation on these problems. And so the piecewise are a little bit trickier because if I'm interested in the limit as x approaches 3, and right here it's showing me that the function is going to change its look at 3, then I have to check the left side of 3 and the right side of 3. This one is happening to the left of 3, what's less than 3, and this little symbol right here will point in the direction that's to the left. So this would be the function that's coming from the left, and this points greater than to the right, so this is the function that's coming from the right. And if I want to find the limit, what has to happen is from the left and from the right, remember these two things have to meet. Oops, a little marker on my finger. These two things have to meet. They have to meet in the same spot. They don't have to meet at the same like shape. They just have to meet at the same spot. And so I'm just going to evaluate the left-hand side and evaluate the right-hand side and see what I get. So when I evaluate the left-hand side, I'll put 3 in for x. I get 3 halves minus 1 half. That's going to be the value I get here. Has to be the same as, I'll evaluate the right-hand side, 3 minus 2. So I'll put 3 in for both sides of the function and see if they actually meet, if they are equal, if they come out to be the same. So 3 halves minus 1 half is 2 halves. 2 halves is 1 equals 1. Yes, they are the same. And if they are the same, then that is my limit. So my limit of this function as x approaches 3 is 1. What if they didn't come out to be the same? What if the left-hand side and the right-hand side don't match? Then the left-hand limit is different than the right-hand limit, and therefore the limit does not exist. What if they're asking only for the left or the right? Well, that's what's going on in this case. And I know my camera is a little blurry. Sorry about that. It's just not a great camera. But on your sheet, it says the limit as x approaches -2 from the right. If you downloaded the sheet, if you're just watching the video, that's what it says. X approaches -2 from the right. And so I'm only interested in this function on the right-hand side. And so up here, I'll look at these. This is to the left of negative 2 because it's less than negative 2. This is the function that's to the right of negative 2, and therefore this is the one that I'm interested in, the one that's to the right of negative 2. Well, I'm really just looking for the limit as x approaches negative 2 of 3. And that's another constant like we saw up above. Remember the constant. Remember, keep that sort of in your back pocket. Know it's there. So the limit of this constant is 3, and therefore my limit from the right is 3. Okay? So sometimes that takes a little practice. These are more intimidating than they really need to be. Just you've got to kind of get over it. We're not graphing them. We don't have to graph them. All we're doing is find the limit of them, so we're directly evaluating. So in this one, I'm interested in the limit as x approaches 0. Well, wouldn't you know it? 0 is where the graph changes direction. And so I need to check to see if on each side of 0, and it's not from the left or from the right, it's both. So I have to check to make sure that on each side of 0, the graph is going to come together and meet. Again, it doesn't have to be the same look. The left-hand side is a parabola, the right-hand side is a line. So this is going to be, if I graph it, this could look like this when I graph it, or it could look like this. It should be a positive line, but you get what I'm saying. If they meet, they meet. If they don't, they don't. And I have to see which one. I don't have to graph. I can check with the math. So what happens when I plug in negative 0 squared plus 1 on the left-hand side and 0 over 2 minus 13 halves on the right-hand side? Well, the left-hand side is 1, and the right-hand side is negative 13 halves, and those are not equal. They're not the same, and therefore my limit does not exist. So let's try another one. Again, this next one is not from the left, not from the right. We just need to check to make sure that they are going to meet, but I have another issue here where all of the rest of these had a breakdown of the function that said, okay, on the left it's this function, on the right it's the function below. On the left it's this line, on the right it's this constant. Well, now we get down to problem number 28, and it doesn't say that. What it says is, it is this line everywhere except at negative 2, and then it's negative 2 at negative 2. So it's this line, kind of looks like this, everywhere except at negative 2, there's this hole in the graph. Well, if we look at that, keep in mind that the limit is not the value, so I don't care what the value is. What I care about is what's happening on each side of negative 2. Where is it headed? Remember, is it meeting on both sides? Well, yeah, it's meeting on both sides. It's meeting at this hole that we took out because that's the adjusted function. It can't be negative 2. For whatever reason, it's undefined there. So even though I'm interested in what's happening at negative 2 on both sides, it just so happens that this function takes care of both sides. And so I can plug that in. The opposite of negative 2 plus 1 ends up being both the left and the right-hand side of the function, and that is at 3, and that kind of looks like about where my graph was maybe graphing, and therefore that is my limit. So don't overthink the piecewise functions too much. Most of the time they can be completed by direct evaluation. You just have to know what you're looking at. If you're comparing a left and a right, make sure that they equal, or if you're only interested in a left hand or a right hand, pick the function that is to the left or to the right, or coming from the left or coming from the right. If it's a function that has an undefined location, then remember that the function to the left and to the right of that undefined location is going to follow the given function that this is everywhere else. And so even though it doesn't equal it there, that's not what a limit is asking. A limit's not asking what's the value. The limit is asking what does it look like the function is doing on each side of that point. And again, here it looks like it's a line going to that hole. So again, that was part 2, section 2 with direct evaluation. Now, it's not always going to come out nice when you do your direct evaluation, and that gets into our next section. What happens if I come up with something that doesn't give me a nice value right away? Okay, so stay tuned for video part 3, where we're going to have to do some manipulation. Thanks for watching. I hope all is well. Again, if you have any questions, just shoot me an email. Have a good one.